Have you ever felt that the universe remembers what we choose to forget? Years ago, an object called 3I Atlas drifted through our solar system, silent, unpredictable, vanishing before we could understand what it was. Scientists called it Interstellar, a visitor from another sun. But now, something else is following the same path. It isn't bright, it isn't loud. It moves like it's hiding, and yet somehow watching. This new body doesn't fit the rules. It releases gas where there should be ice. It flickers where there should be nothing. And its orbit, twisted through the same corridor that Atlas once used, is bending in ways we've never seen before. In tonight's film, you'll discover what connects them, the evidence that was missed, and why astronomers whisper that what's coming next might not be a comet at all. So lie back, slow your breathing, and listen carefully. Because before this night ends, you'll understand why they're saying something worse than 3I Atlas is coming. And before we begin, subscribe to Whisper Science and tell us in the comments from which corner of the world you're watching the universe tonight.
Welcome. You are watching Whisper Science. Make sure to subscribe and join us for more amazing science content. Now, let's move back to the video.
They said we could relax, that the skies were calm again, that the third interstellar visitor, the one they called 3I Atlas, would pass quietly, a harmless traveler brushing past our solar neighborhood before fading into the dark. For a moment, the world believed it. Headlines eased the collective pulse. No risk to Earth, nothing to fear, just another beautiful mystery drifting by. But while the cameras pointed at that glowing stranger, another story was unfolding in the corner of the sky. Faint, hidden, and dangerously close. Something was moving through sunlight itself, cloaked in the radiance that blinds our telescopes. It was never meant to be seen. Yet the sun, in its way, betrayed the secret. A pulse of ultraviolet light scattered just enough for one human eye, an amateur, not a professional, to notice a tremor where there shouldn't have been one. That tremor was a comet, a nameless wanderer, later baptized C/2025 R2, Swan. It was the kind of discovery that begins quietly and ends with questions no one wants to answer. Because when it appeared, it was already leaving the sun, already heading our way. October 20th, 2025. A date marked on no calendar, but burned into every trajectory model within hours of discovery. 8 days away. Closest approach, 39 million kilometers. A comfortable distance, they said, until you remember that cosmic comfort is a matter of scale, not safety. The space between calm and chaos is sometimes just arithmetic. When astronomers ran the orbital calculations, the numbers whispered a truth too small for headlines. R2 had slipped past every warning system we built. It wasn't large enough, bright enough, or positioned right for ground-based telescopes. It hid inside the solar glare, the same region that blinds our most advanced optics, the Heliac blind zone. In that region, the sun itself becomes a curtain, erasing whatever crosses behind it. R2 used that curtain perfectly. For weeks it moved unseen. By the time it emerged, it had already swung around the sun and was on an outbound course through Earth's lane. That's why this isn't really a story about a comet. It is a story about our blind spots, the ones that orbit above us and the ones that live inside us. The irony is painful. We spent months decoding the path of 3I Atlas, that glamorous interstellar nomad from another star, watching it like an invited guest at a cosmic banquet. We drew its arc, modeled its tumbling spin, even speculated on its color shifts and alien origins. All the while, R2 crept through the light behind our obsession, the uninvited guest at the back door. No alarms went off, no urgent bulletins, because in our system an object becomes real only when it enters our instrument's field of vision. Before that, it's a rumor in mathematics, and yet that rumor was already close enough to matter. Imagine this: a body of ice and dust roughly a few kilometers wide, traveling at nearly 30 kilometers per second, its surface boiling under solar radiation, shedding gas and grit into space. You can picture it as a ghost wrapped in a green veil, a halo born from the fluorescence of carbon molecules under ultraviolet light. That glow is beautiful. It's also the mark of volatility, a sign that its skin is cracking, venting, alive in the most dangerous way a rock can be alive. By the end of September, R2 brightened dramatically. Observers who caught it reported that its coma, the glowing envelope of vapor around the nucleus, expanded rapidly. Some called it an outburst, others called it an awakening. Either way, it meant pressure, instability, motion. Comets don't simply brighten because they feel poetic. They brighten because something inside them breaks. So here we are, one comet famous, one almost invisible, one sailing safely at a distance of over 160 million kilometers, the other brushing by at barely a quarter of that. And yet only one dominates the news, the one that isn't a threat. Why? Because the human mind loves spectacle more than proximity. We stare at the far away because the near feels ordinary until it isn't. For all its charm, R2 exposes a deeper vulnerability. Our planetary defense network, the array of telescopes, sensors, and algorithms designed to spot hazardous objects, depends on geometry and timing. It's optimized for what we expect to see: dark rocks against dark space, faint lights moving slowly across the night sky. It's not built to stare into daylight, not built to find things hiding behind the sun. That's where the blind zone lives, and where R2 hid. The discovery came from a satellite that was never supposed to look for comets at all. The SOHO spacecraft, orbiting between Earth and Sun since 1995, carries an instrument called SWAN, Solar Wind Anisotropies. It scans the ultraviolet emissions of hydrogen gas, mapping the invisible flow of solar particles streaming through the heliosphere. It doesn't see comets directly. It sees what their evaporating water leaves behind, a cloud of hydrogen atoms glowing at 121.6 nanometers, invisible to us, but brilliant to SWAN's sensors. Somewhere in those ultraviolet mosaics, an amateur named Vladimir Bazugi noticed a faint moving patch of brightness. It wasn't in the catalogs, it wasn't in the predictions. He cross-checked frames from different days, saw the patch shift against the background, and raised the alarm. When ground observatories confirmed it, the truth fell into place. A new comet already passed perihelion, its closest point to the Sun, and heading outward, right through the plane of Earth's orbit. It wasn't supposed to happen like that. We're used to discovering comets on their way in, not on their way out. The delay cost us critical data. We missed its approach, its early outbursts, the moments when its structure changed the most. We're now watching only the aftermath, trying to reconstruct the cause from the echo. Astronomers estimate its minimum orbit intersection distance, or MOID, at roughly 0.048 astronomical units, about 7 million kilometers. In cosmic language, that's a thread, a hairline gap between paths, perfectly safe in theory, unless theory meets chaos. If a comet like this fractures, the fragments drift slightly from the parent orbit, forming a spread of possibilities instead of a single line. Each piece follows its own destiny, and sometimes destiny curves closer than math intended. That's what keeps people like Bazugi awake at night. Not fear of impact, fear of ignorance. because we cannot defend ourselves against what we cannot see. But there's another layer to this. When something like R2 appears unexpectedly, it doesn't just expose a gap in our sky surveillance. It exposes the rhythm of our own attention. Humanity doesn't look at the cosmos evenly. We look where the light is comfortable, where the data is easy, where the story is exciting. The rest, the blind spots, the background, the silence, we leave to amateurs and accidents. And that's the paradox. The more we automate our vigilance, the easier it becomes to forget what vigilance actually means. Right now, in observatories scattered from Hawaii to Chile, rows of telescopes sweep the darkness every night. Algorithms compare new images to old ones, subtracting patterns, isolating movement. It's a ballet of precision and light, but none of it matters when the target hides behind the sun. No survey can pierce that glare. No detector can map what's lost in brilliance. That's where R2 lived, not in darkness, but in too much light. And maybe that's the metaphor for more than astronomy. Maybe the things most capable of surprising us are not the ones in the shadows, but the ones blindingly illuminated by the very systems meant to protect us. In a week, R2 will glide past and vanish again, heading back toward the frozen outskirts of the solar system, perhaps never to return in our lifetime. But the lesson it leaves behind will linger, a quiet reminder that our sense of security is often just geometry pretending to be certainty. So as we count down to October 20th, the question isn't whether this comet will hit us. It won't. The question is whether we'll notice the next one before it does. Because somewhere in that same zone of light, there could be another traveler. One we haven't seen yet, one that's already inbound. And if we only look where the headlines tell us to look, we'll never see it coming. Every discovery carries a confession. In science, that confession is usually this: we didn't see it soon enough. For Comet C 2025 R2, that delay wasn't measured in months, only in angles, a few degrees of sky. That's all it took to hide an entire celestial body from the planet as collective gaze. To understand why, we have to talk about the geometry of blindness. Telescopes on Earth don't see everything. They can't. Their vision depends on darkness, contrast, and distance from the sun. There's a forbidden cone of brightness, an area surrounding the sun where no optical instrument can safely look. If a comet travels through that cone, it vanishes, not because it's small, but because it's too bright around it to see anything at all. Astronomers call this the solar exclusion zone, or more poetically, the blind arc. That's where R2 lived, hiding in plain radiance. To most people, the discovery of a comet sounds romantic, a flash in the telescope, a scientist gasping, a headline forming. But the truth is colder and lonelier. Modern comets aren't found by the heroic human eye, but by lines of code comparing millions of pixels night after night. Automated surveys like Pan-STARRS, Catalina, and Atlas sweep the heavens, hunting for moving dots. The dots brighten, shift, and reveal orbits. The process is relentless, mechanical, astonishingly efficient, but only within limits. Those surveys depend on contrast, faint points against a black canvas. Shift the object even a little closer to the sun's glare, and it disappears like ink spilled into fire. R2 was that drop of ink. When SWAN, an ultraviolet detector aboard the SOHO spacecraft, caught it, it wasn't even looking for comets. It was mapping hydrogen in the solar wind, tracing the invisible rivers of particles flowing outward from the sun. Every day it takes a picture of the whole sky in ultraviolet light, not visible to the human eye. In that wavelength, hydrogen glows, and comets leak hydrogen by the ton as sunlight breaks their water apart. So when R2 began to shed its veil of vapor, Swan noticed the glow, a ghostly hydrogen halo millions of kilometers wide. To the naked eye, the comet was still invisible. To Swan, it was a beacon. And the one who noticed that beacon wasn't a professional at all. He was Vladimir Bezugi, a name barely known outside small astronomy forums. He spent his nights combing through public Soho archives, hunting for patterns most people overlooked. And in September 2025, he saw something move, a diffuse patch sliding across successive ultraviolet frames, changing position with the rhythm of an orbit. He didn't believe it at first. Few amateurs do. He checked, rechecked, and finally sent a report. That report was the first domino. Within hours, the Minor Planet Center confirmed it. The designation came next, C2025R2 Swan, the letter R marking the second half of September, and the number 2 noting it was only the second comet found that period. But what mattered wasn't the name, it was the timeline. R2 had passed perihelion, its closest approach to the Sun, a day before discovery. We'd missed the main act, the moment of maximum heat, maximum volatility, maximum data, gone. All that remained was aftermath, like stepping into a theater after the explosion and reading the smoke for clues. The implications were sobering. When you detect a comet after perihelion, you lose your best chance to predict its future. Cometary behavior is chaotic, outgassing, spinning, fragmenting. All of it changes trajectory in small but measurable ways. The earlier you see it, the more you can model its forces. But if you arrive late, your data becomes guesswork. The first orbital estimates showed high eccentricity, 0.999, practically a parabola. That meant R2 came from far beyond Neptune, maybe the Oort cloud, the icy shell that marks the solar system's outermost border. It's a realm of ancient debris, remnants of creation, drifting for billions of years, stirred only when something nudges them, a passing star, a wave of galactic gravity or pure statistical fate. And when one of those pieces falls inward, the whole solar system becomes its playground. For a brief moment, as R2 crossed the Sun's orbit, every variable mattered. Its spin, its mass, its composition, its outgassing rate. But the truth is, we didn't know any of them. We had numbers, not knowledge. The ground surveys tried to catch up. Observatories in Chile, Arizona, and Japan pointed telescopes toward its coordinates. They found it, a faint green smear in the pre-dawn haze. The green was classic, diatomic carbon fluorescing under ultraviolet radiation, the chemical signature of nearly every active comet. But what unsettled astronomers was its asymmetry, one side of the coma brighter than the other, as if the comet was venting gas from a single wound rather than evenly across its surface. That meant one thing: instability. Something beneath the crust had cracked open. Imagine standing on an icy world a few kilometers wide, sunlight blasting its surface after eons in the dark. The frozen gases trapped beneath, carbon monoxide, methane, ammonia, start to boil. The surface buckles. A geyser of vapor and dust erupts into space, spraying thousands of tons of material each second. That jet acts like a thruster, pushing the nucleus slightly in the opposite direction. Not much, just a few centimeters per second. But at cosmic distances, that's the difference between safety and collision. Every jet, every fracture, every grain of dust changes the path, and those changes accumulate. This is what astronomers call non-gravitational forces, the subtle nudges from within that alter a comet's fate. In the case of R2, those forces were largely unknown. We didn't observe its pre-perihelion outgassing. We had no baseline. We were flying blind through equations. Weeks later, as more data arrived, the models improved, but the questions grew. The orbit was inclined by just 4.5 degrees, almost flat, aligned with the planetary plane. That made it unusual. Most Oort cloud comets dive in from random angles, steep and fast. R2 was different, more like a planetary wanderer than an interstellar drifter. That low inclination put it right in the ecliptic neighborhood, the plane where Earth and most of the planets move, which also meant it would stay there longer. That proximity makes for good observation and bad odds, because when you spend more time near the planetary plane, the statistical chance of crossing another planet's orbit goes up. For Earth, that intersection distance, the MOID, was razor thin, just 7 million kilometers. Nothing catastrophic, but uncomfortable. In meetings at NASA's Center for Near-Earth Object Studies, the conversation wasn't about impact. It was about process. How had this object slipped past every ground-based survey until the last moment? How could a hydrogen mapping camera, not even designed for comet discovery, find what the world's largest telescopes didn't? And more importantly, how many others were hiding right now, invisible in the daylight? The answer was the same one astronomers always give: we don't know. But beneath that admission lies a truth more human than scientific. We build detection systems to feel safe, not to be perfect. And every time a new comet slips through the net, it forces us to confront what safe really means. The lesson wasn't lost on the professionals. Within days, SWAN's data streams were re-examined. Dozens of amateurs dove into the archives, hoping to find more hidden comets lurking near the sun. A few faint anomalies appeared, all dismissed as noise. But one of them, weeks later, turned out to be real. Another small object, another near miss. And so the cycle continues. Discovery by accident, correction by hindsight. The public, meanwhile, saw only the headlines: another spectacular comet approaches Earth. Without realizing the story, its real headline should have been, "We almost missed it." That's what makes R2 different. Not its brightness, not its path, but its timing. We spotted it just late enough to remind us how fragile our perception really is. The world's telescopes are like neurons firing in the brain of civilization. They see, process, and react. But if the input arrives too late, even by seconds, the response loses meaning. The system works perfectly, only after the danger has passed. And maybe that's the heart of this story. Not about a comet at all, but about the limits of attention, cosmic and human alike. R2 isn't the villain, it's the mirror, because it's not asking if we can detect threats. It's asking when we'll notice them, and whether soon enough is even in our vocabulary anymore. The first images of R2 after discovery were ghost-like. A faint emerald haze suspended above dawn's horizon, shimmering against the last breath of night. For casual observers, it was beautiful. For astronomers, it was unnerving. Beauty in space is rarely gentle. A comet that glows green is one that's alive in all the dangerous ways an object can be alive: boiling, cracking, changing, unpredictable. By mid-September, just days after its unveiling, R2 began to behave like something restless. Its brightness spiked, dipped, and spiked again, patterns that didn't match the simple equations used to forecast comet magnitude. In the official logs, you can trace the astonishment line by line. Unexpected increase in apparent magnitude. Possible outburst event. Coma expansion continuing beyond model predictions. Translation: something inside the comet was moving. To the human eye, The green glow was the telltale breath of diatomic carbon, a molecule that fluoresces under ultraviolet radiation. But to scientists, it was the comet's confession. Carbon isn't released unless the surface ice fractures, venting gases that had been sealed for millions of years. That meant the nucleus was active, violently so. R2 wasn't behaving like a frozen relic merely reflecting sunlight. It was reacting. Its rotation, its internal pressure, its structure, all were changing in real time. And that's when astronomers realized they were late to the story. The main outburst had probably already happened, hidden behind the sun's glare weeks before detection. What they were watching now was the aftershock, a body still trembling from its own awakening. If you plotted its brightness curve over time, it didn't look like a neat bell. It looked like a heartbeat, jagged, uneven, alive. That pulse told a story of struggle. The comet had survived its perihelion passage, but not unscarred. Something had broken open inside it, maybe just a small vent, maybe an entire section of crust collapsing as trapped gases forced their way out. Every possibility led to the same conclusion: instability. In deep space, instability means evolution. A comet that sheds gas unevenly begins to wobble. A wobbling nucleus alters its spin rate. A changed spin rate distorts sunlight exposure, and sunlight exposure drives sublimation. Each reaction feeds the next. In the language of celestial mechanics, this cascade has a name: non-gravitational acceleration. Most objects in the sky move exactly as gravity tells them to. Comets are the rebels. They thrust themselves forward by venting. Every jet of vapor becomes a miniature engine. Sometimes the push is gentle, a steady plume lifting dust like breath from a candle. Sometimes it's violent, a detonation that changes everything. No one could say which kind R2 carried, but the data hinted at chaos. Images from late September revealed a tail that refused to behave. Instead of a clean stream pointing directly away from the sun, R2's tail forked and twisted, like threads caught in a storm. One moment narrow, the next diffuse, sometimes bending at odd angles. These weren't illusions of optics. They were structural expressions of something real, jets firing from different vents at different times, from a spinning body that no longer rotated smoothly. It's hard to overstate how unsettling that is for astronomers. Comets are fragile to begin with, collections of dust and ice bound by little more than cohesion and faith. When their spin goes irregular, their internal stresses rise exponentially. A few extra rotations per day can rip them apart. Somewhere in those nights of green haze and trembling data, a quiet question began circulating among researchers. Was R2 already breaking? The public, of course, didn't hear that part. News outlets framed the event as spectacle. A new naked-eye comet is gracing our skies. Look east before dawn to glimpse a cosmic wonder. Few noticed the tone in the scientific bulletins: tight, clinical, cautious. Brightness curves with warnings about uncertainties. Models annotated with asterisks. The excitement of discovery mixed with the anxiety of something we didn't control. By early October, R2 had reached magnitude 6, barely visible to the naked eye but brilliant through binoculars. The coma, once a compact sphere, now stretched across half a degree of sky, roughly the apparent size of the moon. And yet, buried inside that halo, the actual nucleus remained unseen. Too small, too faint, too shrouded in its own debris to reveal its shape. All we had were shadows and guesses. Estimates suggested a nucleus a few kilometers across, maybe 3, maybe 5. But that's the kind of uncertainty that haunts trajectory calculations. A smaller body outgasses faster and changes orbit more dramatically. A larger one resists those forces but carries more mass and therefore more momentum if fragments break off. Either way, it wasn't just an aesthetic curiosity, it was a physics problem with consequences. Think of it like this. Each grain of dust, each pebble thrown from R2's surface, inherits the comet's motion, but not perfectly. A difference of even 1 meter per second compounds over millions of kilometers. After days, those grains form a plume. After weeks, they form a sheet. After months, a field, a drifting highway of debris. Now imagine Earth's orbit slicing through that highway. The distance between safety and impact isn't always a number. Sometimes it's a phase. If the comet and Earth arrive at the same node of intersection at the same time, they meet. If they don't, they miss each other by comfort's width. But the fragments, the dust and gravel, don't follow strict schedules. They spread out like fog. So even when a comet's core is safe, its debris can still touch us. That's how meteor showers are born. But meteor showers are also how we discover how close we came to disaster. With R2, that risk isn't a doomsday scenario. It's a reminder. A demonstration of probability made visible. The thin margin between spectacle and threat. Late September brought one image that defined R2's personality. An astrophotograph from Spain showing the comet's coma shimmering green against twilight. The tail rose upward like a spectral flame. Below it, the sun had already set. That picture spread across astronomy forums, accompanied by poetic captions. But in research circles, the caption was different. Signs of increased dust production. In space, dust is warning, not wonder. Increased dust means the nucleus is shedding mass faster. It means structural integrity is weakening. It means the comet is tiring, dying in slow motion under its own brilliance. And so the narrative began to shift from discovery to diagnosis. Was R2 fragmenting? Had it split already? High-resolution imaging from several observatories tried to answer that question. Most showed no clear multiple nuclei, but some recorded subtle condensations. Denser pockets of light near the center of the coma. Were those artifacts or tiny fragments still hugging the main body? Nobody knew. This uncertainty threaded through every conversation. Some astronomers compared it to Comet 73P Schwarzmann-Wachmann, which began fragmenting in the 1990s and now travels as a train of mini-comets, each following slightly different paths. Others mentioned Comet Lenin, which disintegrated in 2011, turning from a promising spectacle into a cloud of nothingness before it ever reached perihelion. R2 could end like either or neither. And still, as October deepened, it held together. If it was breaking, it was doing so quietly, gracefully, hiding the cracks beneath its halo. By October 10th, magnitude reports placed it at 6.7, a faintness that hinted at either exhaustion or stability. It hadn't brightened again. It hadn't faded entirely. It was just holding. That equilibrium, fragile as it was, offered temporary comfort. But comfort in comet science is deceptive. When an object stabilizes after an outburst, it can mean one of two things. It has settled into a steady venting rhythm, or it has sealed itself again, building pressure for the next explosion. Astronomers waited. Each night they compared photometric readings, searching for another sudden jump, another tremor in the light curve. Nothing yet. But the silence itself began to feel ominous. Because silence in a system built on instability rarely means peace. Somewhere out there, The green wanderer continued its path, a survivor maybe, or a ticking clock, its coma thinning, its dust drifting behind like a fading signature. And in every telescope that caught a glimpse of it, the same question lingered. Is this how near misses begin? We've learned to quantify uncertainty, assigning probabilities, margins of error, confidence intervals. But no statistic can capture what it feels like to watch something fragile drift through the edge of Earth's cosmic neighborhood, unpredictable, unresolved, and late to the party. In the coming days, R2 would approach its closest distance, barely 39 million kilometers, safe on paper. But the numbers weren't what haunted astronomers. What haunted them was what they didn't know. The true size of the nucleus, the hidden cracks, the fragments too small to see. Because in astronomy, you can't defend against what you don't detect. And for all our telescopes, satellites, and simulations, we're still staring through keyholes at a universe full of locked doors. Numbers have a way of sounding safe. They sit there on the screen, clean, silent, obedient. But in orbital mechanics, numbers lie through omission. They whisper certainty where only chaos exists. The truth about R2 isn't hidden in poetry or speculation. It's written in decimals, tiny, trembling digits that decide the difference between beauty and disaster. Astronomers call them elements, eccentricity, inclination, perihelion distance, semi-major axis. To most people, they're meaningless. But to those who understand them, they're destiny in mathematical form. R2's orbit is a needle stretched almost perfectly straight. Its eccentricity, 0.9993, puts it just shy of a parabola, the curve of no return. That number alone tells us this comet didn't originate here. It fell from the Oort cloud, a frozen sphere of debris encircling the solar system, where the sun's gravity fades into interstellar night. Objects out there drift for millions of years in near silence until something nudges them. A passing star, a ripple in the galactic tide, the faint heartbeat of distant gravity. Then, one begins its long fall inward. When R2 was nudged, it started a journey that took perhaps 20,000 years. 20,000 years of free fall for a few weeks of spectacle. It entered the inner system along an orbit tilted barely 4.5 degrees, nearly flat compared to Earth's path. That's rare. Most comets from the Oort cloud dive in steeply at awkward angles. R2 came in low, smooth, subtle, like a shadow moving along the floor rather than across the ceiling. That low inclination is what unsettled scientists most. It meant R2's trajectory didn't just brush through the solar system. It lingered in the same plane as the planets. It would pass close to the orbital highways we travel every year. Think of the solar system as a massive, invisible racetrack. Each planet speeds around the sun in its own lane. Normally, comets cross that track at sharp angles, appearing like sparks flying through traffic. But R2 entered the same lane. For a brief moment, we shared the same path, different times, same coordinates. That coincidence of geometry produces the metric every astronomer dreads and obsesses over, the minimum orbit intersection distance, or MOID. For R2, it's about 0.048 astronomical units, just over 7 million kilometers. That's 20 times the distance to the moon. In cosmic terms, that's a whisper. It means the comet's orbit and Earth's orbit are separated by the width of a sigh. As long as timing keeps them offset, we're fine. But timing is fragile. The predicted closest approach, October 20th, 2025, puts R2 about 0.26 astronomical units, or 39 million kilometers from Earth. Safe, a cosmic miss. But the word predicted hides a quiet truth. Prediction depends on data, and our data began late. The earlier you observe a comet, the tighter the orbit solution. Every new measurement narrows the cone of uncertainty. We met R2 halfway through its act. That means our cone is wide. If you plotted all possible trajectories, you wouldn't get a thin line. You'd get a shimmering band, a blur of potential futures fanning outward from our best guess. Within that blur, small perturbations can bend reality. A single outburst, one vent releasing a jet of gas at the wrong angle, can shift the orbit by hundreds of kilometers. A minor fragment detaching from the nucleus changes the center of mass, altering momentum. The comet becomes its own unpredictable engine. And unpredictability is what physics hates most. We calculate trajectories assuming the universe plays fair. Forces are consistent, gravity is constant, sunlight is steady. But comets aren't fair players. They carry their own chaos inside. Every time R2 outgasses, the simulation must adapt. Every time a plume erupts, the future bends. NASA's orbital models factor this in. They assign non-gravitational parameters, coded as A1, A2, A3, describing thrust in 3 directions. But those numbers are based on past observations. We don't know the future behavior until it happens. And by the time it happens, the numbers change. So even with perfect math, the cosmos keeps secrets. To visualize it, imagine a thread stretching from the sun outward. Earth moves along one thread, R2 along another. They come closest at a single crossing point, one intersection in space. But what matters isn't the crossing, it's the timing. If Earth passes that point weeks before or after R2, we're safe. If they sync up, just once, just wrong, it's no longer theoretical. Astronomers call that timing mean anomaly. Philosophers might call it fate. The numbers reassure us now. The dates don't align. The paths miss by millions of kilometers. But behind those calm figures hides a question that never really sleeps. What if the data is off by just a little? Because in cosmic arithmetic, small doesn't stay small. Consider this. If a fragment the size of a mountain breaks off R2, it doesn't keep the same orbit. A difference of 0.00 matter in trajectory may sound microscopic, but after a few million kilometers, that's a separation of thousands of kilometers. Multiply that by time, and the debris spreads into a long ribbon of uncertainty. We might not hit the comet. We might just hit its shadow. Meteor showers are gentle versions of that shadow. They were proof that comets leave trails dense enough to paint the sky with fire when Earth passes through. Most of the time, it's harmless, a spectacle. But every meteor shower is also a reminder. At some point in history, a comet's path and ours crossed exactly. For R2, that thought lingers like static behind every calculation. When the orbit was first released to the public, it carried error bars. Small deviations in perihelion timing, inclination, argument of periapsis. Those numbers mean almost nothing to anyone outside the field. But to orbital dynamicists, they represent how much the universe could still surprise us. If those margins stretch just a little, a debris trail could intersect Earth's position weeks or months later. The probability is microscopic, but not zero. And in cosmic safety, not zero is enough to matter. The challenge isn't panic, it's precision. Every night since the discovery, observatories have tracked R2, adding new astrometric points to refine the orbit. The error bars shrink. The trajectory sharpens. The models agree. It will pass safely. But even when certainty grows, doubt persists. Not in the math, but in what math can't yet know. There's a famous saying among astronomers, the sky always wins. It means that no matter how good the models, the universe gets the final word. R2's numbers look stable now. But so did Comet Shoemaker-Levy 9 before Jupiter tore it apart in 1992. So did Comet C2019Y4 Atlas before it disintegrated weeks before perihelion. Predictability is an illusion until it isn't. And yet, this is what we do. We stare at decimals and convince ourselves they're prophecy. Perhaps that's part of the human condition, the need to find comfort in the measurable, even when standing on the edge of the immeasurable. In every control room, every observatory, every midnight monitoring session, there's a strange mix of awe and anxiety. Scientists are not immune to emotion. They just translate it into units. When an astronomer looks at R2's orbital diagram, they don't see a simple ellipse. They see a living system, a dance of uncertainties twisting through space. They see the ghost of every calculation that might one day fail. And somewhere between those equations and that fear, there's wonder too. Because even in its danger, a comet is a messenger, a fragment of creation itself, still burning with the memory of how the solar system began. That's the paradox that keeps us watching. The thing that could destroy us is also what made us. R2 won't collide. The numbers, for now, hold steady. But as its tail grows longer and its fragments scatter behind, Earth spins beneath a sky that forgets nothing. Every pass, every outburst, every dust grain joins the archive of near misses, the quiet history of almost that defines our survival. So when we look at those numbers on a glowing monitor, we're not really asking, will it hit? We're asking, how many more won't? Because in a universe, this vast near misses are not accidents, they're tradition. October has always been a noisy month for the sky. Even when nothing unusual happens, it's when the heavens seem busiest. Meteor showers, conjunctions, the quiet migration of planets across dawn. This year, though, the noise is literal. 2 comets are visible at once and the world can't stop looking up. Every camera is pointed at C2025R2, or at least at where someone said it should be. The rest are pointed at another visitor, C2025A6 Lemon, climbing through the northern hemisphere with its own pale green glow. The result is chaos wrapped in beauty, a double spectacle, both objects peaking within days of each other, both promising wonder. And right in the middle of their crossing, the Orionid meteor shower begins to fall. If you could step outside on the night of October 20th, you'd see streaks of light tracing the darkness, tiny particles from Halley's Comet, burning up as they slam into Earth's atmosphere at 70 kilometers per second. The air itself turns into fire. It's breathtaking, and that's the problem, because when the sky performs, we stop listening. Headlines overflow with words like celestial show, double comet, once-in-a-lifetime view. The anchors smile, the graphics sparkle, and the collective heartbeat of the planet slows into awe. No one asks what's hiding inside that beauty. The same week that R2 passes its closest approach, news anchors talk about rare alignments and the dance of cosmic visitors. What they don't talk about are uncertainties, those thin margins of orbital doubt, the fragments we haven't seen, the debris spreading invisibly along a path we barely mapped. And why would they? Spectacle sells. Uncertainty doesn't. It is easier to tell people where to look than to tell them why they might be looking in the wrong direction. Astronomers know this tension too well. Every discovery comes with 2 versions, the one for science and the one for the world. In science, R2 is a dataset of late detection, of missing early phase observations, of unknown spin vectors, and incomplete photometry. In the world, It's a glowing wonder, something to photograph and forget. But under that glow, something else is unfolding. The comet's coma continues to expand, feeding a dust tail that grows fainter but wider. Its phase angle, the geometry between the Sun, Earth, and the comet, shifts, causing brightness variations that make amateur observers think it's pulsing like a heartbeat. In reality, that flicker is geometry mixed with dust, sunlight scattering unevenly through a cloud of debris we can fully measure. And buried in that flicker, there might be fragments. Nobody wants to say it on camera, but every astrophotographer who stacked their images in software knows what they've seen. Slight deviations in brightness near the nucleus, subtle elongations that might be image noise, or might not. The professionals are cautious. When something can't be confirmed, it's labeled uncertain structure. It is a polite way of saying, we are not sure if it is breaking. Meanwhile, the public fascination turns toward 3i Atlas again, the interstellar celebrity still coasting far beyond Earth, perfectly harmless, but infinitely more mysterious. It dominates headlines, documentaries, comment threads. Everyone loves an interstellar story. It feels poetic, cosmic, almost spiritual. R2, by contrast, is domestic, a local wanderer, one of our own. And humans have never been good at fearing the familiar. So while the world celebrates the beauty of the double comet event, few notice the deeper irony. The one closer to us, the one slipping through our defenses, is the one nobody's talking about. That isn't just a failure of media. It's a reflection of how we see danger itself. Our species has a peculiar blindness. We fear the alien because it feels foreign, yet we ignore the threat next door because it feels routine. The same psychology that makes us obsessed with 3i Atlas, the faraway, the otherworldly, is what lets R2 slip past without notice. In a press briefing that never made it to mainstream air, a NASA spokesperson admitted it plainly. C-2025 R2 is not an impact threat, but its late discovery highlights ongoing gaps in solar proximate detection. Translation: we found it late, and next time we might not be as lucky. But that sentence never trended. Instead, feeds filled with time-lapse reels of the Orionids, of comets glowing like emerald embers, of captions reading, "Look up tonight, the universe is alive." And yet, the universe was never more silent. Because behind that celebration, real work was happening in the dark. The Minor Planet Center, JPL, ESA, and countless independent observatories spent the week refining orbital elements for R2, feeding updated astrometry into their models. Each refinement brought reassurance. No collision, no debris crossing, no reason to panic. But reassurance isn't immunity. They know how easily the next R2 could slip by unseen, following the same blind route through solar glare. The system we built to protect us is brilliant, but it's also brittle. It relies on open sky, clear weather, and predictable motion. It relies on instruments that can't stare too close to the sun without burning their sensors. And it relies above all on human attention, something that can be distracted by a headline or a meteor shower. That is the real danger of a sky full of wonder. The more there is to see, the less we truly notice. R2 isn't unique in this pattern. History repeats the same quiet warning again and again. In 2013, a small asteroid exploded over Chelyabinsk, Russia, injuring more than 1,000 people. No one saw it coming. It approached from the direction of the sun, invisible to every telescope. In 2022, another object only a few meters wide was discovered hours before it entered Earth's atmosphere. These are not failures of technology. They're reminders of geometry. The cosmos doesn't care where our telescopes are pointed. R2's late discovery is a modern echo of that truth. Another reminder that the danger isn't what we see, it's what we miss because we were looking elsewhere. And now, as the double comet display peaks, it's happening again. People gaze up in wonder, unaware that while they watch 2 comets and a meteor shower, a dozen smaller objects are moving invisibly between planets, too faint, too fast, or too sunlit to detect. Every bright distraction is also a curtain. Behind it, something quieter waits. This isn't cynicism, it's reality. Astronomy at its core is the science of patience and probability. It's not about seeing everything, it's about knowing that you can't. R2 will fade from view soon. Its dust will disperse, its tail will dissolve, and the world will move on. The photographs will remain, the hashtags will die, and by the time the next comet appears, this one will already belong to history. But history doesn't delete its lessons, it buries them. When the light shows end, scientists will gather in small rooms, running simulations of near-Sun comets, calculating detection coverage, and arguing about funding for instruments that can stare directly into glare. They'll talk about solar elongation limits and UV detection thresholds. They'll write papers filled with data points and cautionary notes, and those papers will rarely make the news, because by then, something else will be shining. The pattern is predictable. Discovery, excitement, dismissal, amnesia. Every cycle repeats until one doesn't. The irony is that even now, R2 isn't our greatest threat. It's just the messenger. A fragile reminder of what we almost didn't notice, and what else might be hiding behind the next sunrise. In the end, the danger is never the comet in the sky. It's the comfort it leaves behind when it fades, because comfort is where vigilance goes to die. Every civilization measures time by the things it almost lost. For us, those near misses drift in silence above our heads, forgotten in the same space that could one day erase us. We remember impacts from the distant past, Chicxulub, Tunguska, Chelyabinsk. But what we forget are the near ones, the invisible near collisions that rewrite our probabilities, but never our headlines. If you list them chronologically, the pattern is haunting. March 2004, asteroid 2004. FH brushes past Earth at a distance of only 43,000 kilometers, closer than many satellites. It's discovered 2 days before. June 2002, a rock the size of a house, 2002 MN, passes within 120,000 kilometers, seen only after it's gone. January 2019 AS5, 10 meters wide, slips past undetected until 9 hours before closest approach. July 2020, QG flashes by at just 2,150 kilometers, the closest recorded non-impact flyby in history, and we find it 6 hours later. Each event should have been global news. Each was treated as a footnote. It's not that we're careless, it's that we're human. Our eyes evolved for forests, not for infinities. We're good at noticing motion across a horizon, not trajectories across a solar system. When you live under atmosphere and sunlight, it's easy to forget how narrow your field of vision really is. Our telescopes, magnificent as they are, share that blindness. They're built to look outward at night, not inward toward the sun. Anything approaching from the direction of daylight is effectively invisible until it's too late. We call it the sunward gap, and it's the single most dangerous blind spot in planetary defense. It's where R2 came from. That realization alone makes astronomers uneasy. The same geometry that hid C2025 R2 could just as easily hide something far denser, darker, faster. An asteroid with no coma, no glow, no warning. Asteroids are different from comets. They don't shimmer. They don't announce themselves with tails or hydrogen halos. They're black stone, the color of burnt iron, almost indistinguishable from the void. When sunlight strikes them head-on, the glare washes them out completely. That's why the Chelyabinsk impact in 2013 caught the world off guard. A 20-meter asteroid entered Earth's atmosphere at over 19 kilometers per second, exploding with the energy of 500 kilotons of TNT. Windows shattered across 6 cities. People were thrown to the ground by the shockwave. No one saw it coming because it approached from the sun. If that rock had been slightly larger, it could have leveled a region. If slightly smaller, it would have gone unnoticed. That's the scale we live between. And it is not a question of if it happens again. It is a question of when. NASA's Planetary Defense Coordination Office tracks thousands of objects, but the truth is painful. Our catalog is incomplete by an order of magnitude. We've mapped nearly all of the kilometer-sized threats, extinction class, but only a fraction of the 100-meter range, the city killers. Anything smaller than 50 meters is largely invisible until it's practically at our doorstep. Imagine that. The entire species dependent on telescopes that can see the difference between safe and 6 hours. There's a kind of humility that comes with that awareness. When astronomers discuss these odds, they don't sound afraid. They sound reverent, because they know what it means to stare at a universe that doesn't owe you notice. The failures aren't technological alone. They're philosophical. We build systems that reflect our psychology. Reactive, not proactive. We wait for light to reach us before we believe something exists. We measure safety in hindsight. That's why comets like R2 feel poetic. They remind us that discovery and danger share the same border, the moment something becomes visible. Behind every successful detection is a field of missed ones, and behind every near miss, a quieter truth. We only survive by accident. Consider 2009 DD45, 40 meters wide, detected 2 days before a pass of 72,000 kilometers, or 2018 VP1, which grazed Earth's orbit 3 times before we noticed, or 2019 OK, which swept by at lunar distance, discovered the day before glowing faintly in a patch of sky everyone thought had been scanned. Each time the world got lucky, and each time the algorithms improved, just a little. But the sky doesn't repeat conditions. Every orbit is unique, every blind spot is temporary, then reborn somewhere else. To solve this, scientists have begun to build eyes that can look where ours can't. NASA's NEO surveyor, set for launch later this decade, will observe in infrared, detecting heat rather than light. It will be able to spot objects hiding near the sun, glowing faintly from absorbed solar radiation. Europe is working on its counterpart, FlyEye, a wide-field telescope designed to catch motion across the bright twilight. Together, they represent a kind of planetary introspection, humanity learning, slowly, how to look at its own vulnerability. But until those systems come online, we remain in the old rhythm, the rhythm of late discovery, the rhythm that let R2 drift through the Heliac blind zone without a whisper. If the comet had been a solid rock, not a cloud of ice, it might have been too dim to detect even after perihelion. If its path had shifted slightly inward, its fragments could have crossed ours. If its jets had erupted asymmetrically, they could have altered its orbit by tens of thousands of kilometers. Each if is a reminder that physics doesn't negotiate. And yet, there's a strange peace in this knowledge, because even in that uncertainty, there's meaning. R2's appearance isn't just a warning, it's a calibration. It shows us where our systems fail and how our curiosity still saves us. When the comet was finally plotted, observatories around the world responded with precision, cooperation, and quiet awe. They didn't panic. They calculated. That's the essence of science. Not control, but comprehension. Still, comprehension isn't protection. The universe doesn't sign treaties. So we keep building better eyes, stronger models, faster alerts, knowing full well that somewhere beyond that horizon, another object is already inbound, unseen, indifferent. In a way, that indifference is what makes space honest. It doesn't threaten us out of malice, it simply is. The sky doesn't care whether we watch it or not, and that's what terrifies and fascinates us in equal measure. Every telescope, every comet, every fragment, they're mirrors showing us who we are when we look beyond ourselves. We stare at R2 and see a rock, but really, we're seeing our own reflection. Small, temporary, orbiting through chance, pretending we understand infinity. When you realize that, the fear fades, it turns into something quieter, respect. Because if the universe ever truly wanted to end us, it wouldn't need to warn us first. And yet here we are, still looking up, still asking questions, still building systems that whisper into the dark. We're listening. For thousands of years we have looked at the sky and seen ourselves. It's not stars we recognize, it's reflection. The constellations we drew were never about the heavens. They were about order in chaos, meaning in darkness, comfort in scale. When we trace a line between dots of light, we're not mapping the cosmos, we're mapping the human mind. And yet the mind that maps is also the mind that fears. Every comet that has ever crossed human sight has carried both beauty and dread. The ancients called them harbingers. To them, comets were not celestial bodies but messengers. Omens of kings falling, plagues beginning, wars brewing. The sky was a mirror of fate, and a comet was the crack running through it. Even today, that superstition hasn't vanished. It just changed costumes. Now it wears the language of science, data, and headlines. When R2 appeared, people didn't tremble in temples, they clicked. They watched simulations, shared images, and whispered in comment sections about signs and end times. The tone has evolved, but the instinct remains. We still want comets to mean something, because meaning gives fear a shape. The universe is indifferent, and indifference terrifies us. So we fill the void with narrative. Celestial visitors become metaphors, coincidences become symbols, and that's not wrong. It's human, but that same instinct blurs something vital. Awe and fear are not opposites. They are twins. Every time we feel small under a sky full of stars, that feeling is a quiet surrender. It's the same sensation our ancestors felt when they mistook comets for gods. The realization that we are temporary, fragile and luminous all at once. That's why a comet like R2 strikes such a deep chord, even when it poses no threat. It carries something we rarely confront, the living reminder that the universe doesn't revolve around us, and yet we are somehow part of it. It's strange how fear sharpens curiosity. The moment something feels dangerous, we lean closer. We want to know. We need to know. That's what drives the scientists. Not safety, but wonder in proximity to danger. R2 is just another ice fragment to a telescope, but to the human spirit it's theater. A slow, silent performance in which the stakes are existence itself. You can sense it in the late-night observatories, the quiet hum of machinery, the soft glow of monitors, the gentle voice of a researcher calling out coordinates into the stillness. They're not just collecting data, they're listening to the universe, to themselves, to that fragile space where awe and fear merge into focus, because that's what the cosmos demands of us, attention. But attention comes at a cost. You can't look at infinity for long without it looking back. That's what happens to people who spend their lives studying things like R2. They start to think in geological time, in orbits that stretch beyond lifetimes. They begin to see civilization itself as a kind of comet, bright, temporary, burning its resources as it approaches its own perihelion. And when they look at Earth from that perspective, everything feels both miraculous and fragile. They see a species capable of predicting celestial motion to the second, yet still unable to predict its own behavior beyond the hour. They see minds that can decode the chemistry of a comet's tail, yet still fight wars over lines on maps. They see the paradox of intelligence itself, how clarity in one realm can coexist with blindness in another. Maybe that's why cosmic threats fascinate us so deeply. They level everything. They remind us that hierarchy, conflict, politics all dissolve in the shadow of a single incoming rock. A comet is democracy by destruction. It doesn't discriminate. It doesn't choose. It reminds us that survival isn't a moral victory. It's just probability playing favorites. That realization, dark as it is, births something extraordinary. Empathy. In the face of a shared threat, humans remember how to be one thing. We did it during the Chelyabinsk explosion. We did it when Shoemaker Levy 9 shattered across Jupiter's atmosphere, and we realized how lucky we were that it wasn't us. We did it briefly, when telescopes caught the flash of an asteroid grazing the upper atmosphere, and for 1 second, everyone online said the same word. Wow, it's almost poetic that we need danger to remember wonder, because wonder without fear becomes arrogance, and fear without wonder becomes paralysis. We need both to see clearly. That's what R2 gives us. Not a reason to panic, but a reason to feel somewhere. A child looked up for the first time and saw that faint smear of green light and whispered, "What is that?" And somewhere else a scientist answered, "It's us, just moving slower," because that's what comets really are, pieces of everything we once were. They hold the ingredients of life, water, carbon, amino precursors, frozen since the dawn of the solar system. When they burn in sunlight, they're not dying. They're releasing memory, the same memory that built oceans and clouds and breath. Every drop of water in your body was once dust like that, drifting through cold space until a collision made you possible. When we look at R2, we're watching ourselves, a version of our origin, still traveling, still dissolving, still whispering, "This is where you came from." That's why fear turns to quiet awe. Because deep down we know the universe isn't trying to destroy us. It's trying to remind us what we are. In that light, every comet is a form of conversation. Not between stars, but between past and present. Between silence and awareness. And maybe that's why discovery always feels spiritual, even when wrapped in numbers. Because what we're really discovering isn't the comet. It's the capacity within us to keep wondering, even when the sky could fall. You can hear it in the soft click of a telescope's shutter, in the rustle of paper, as an astronomer records a new coordinate, in the hushed voice of a student seeing their first comet trail streak across the dark. Those sounds aren't about fear, they're about belonging. R2 isn't just passing through space, it's passing through consciousness. Every pair of eyes that looked at it added another orbit to human awareness. And when it fades, as it soon will, what remains isn't the object, it's the connection. That's the quiet truth science rarely says aloud. We study the cosmos not to control it, but to remember that we are part of it. That's why every discovery feels holy, even without gods, and every comet, no matter how small or safe, carries a sermon written in motion. Look up. You still exist. You still don't understand. Keep trying. The first thing to vanish was the color. By the second week of November, the vivid green halo that once defined C2025 R2 had dulled into a pale, bluish mist. The comet that had once shimmered like an emerald ember was now barely distinguishable from the faint star fields it drifted through. To the naked eye, it was gone. To the instruments, it had only just begun speaking, because sometimes the most revealing phase of a comet's life isn't when it shines, it's when it fades. As R2 receded from the sun, its coma began to collapse. The gases that once expanded into a luminous cloud now condensed, losing fluorescence as solar radiation weakened. Yet the data streaming from observatories showed something strange: the hydrogen Lyman alpha flux, the ultraviolet signal that Swan used to detect it in the first place, didn't decline as quickly as expected. In fact, for several days it remained stable, as though the comet were still releasing hydrogen, despite having moved far enough from the sun that sublimation should have slowed dramatically. That shouldn't happen. Not unless something else was contributing to the signal. So at first, scientists dismissed it as instrument noise, background radiation, solar variability, or a software calibration artifact. But when cross-checked with data from independent observatories, the anomaly persisted. Something was off. The comet was dimming visually, but remained bright in ultraviolet, an inversion of normal behavior. And the hydrogen cloud itself appeared asymmetric, as if expanding preferentially in one direction. No one said it out loud, but everyone thought it: fragmentation. When a comet breaks apart, smaller fragments expose fresh ice to sunlight, releasing volatile gases even as the main body cools. To an instrument like Swan, that pattern would look exactly like what they were seeing: a decaying but strangely consistent hydrogen signal. But there was another possibility, quieter and far less certain. Some data hinted at multiple emission centers, not aligned along the comet's orbital vector. In simpler terms, there might be more than one source. That's when whispers began circulating in research channels. Maybe R2 wasn't alone. It wasn't a conspiracy, just curiosity. Several observatories in Japan, in Chile, and one in Poland noticed faint, moving glows slightly offset from R2's predicted position. They were too dim to confirm as separate nuclei, but too consistent to ignore. In most cases, such anomalies are easy to explain: residual dust, instrumental artifacts, cosmic rays streaking across CCD sensors. But this time, the timing was uncanny. 3 independent instruments on 3 different continents recorded the same deviation within hours of each other. Not identical, but aligned. When plotted, the anomalies traced a faint arc, a subtle curvature just trailing R2's path, offset by roughly 0.01 astronomical units. A thread of light following a fading comet. Officially, nothing was confirmed. Unofficially, the community called it the Echo. No one agreed on what it was. Some thought it might be a fragment cluster, small pieces that had detached earlier during R2's perihelion outburst, now catching sunlight differently as they rotated. Others suggested it was a trick of geometry, a reflection of the comet's tail seen through solar scattering angles. A few speculated something more radical. Perhaps R2 was part of a binary nucleus, 2 bodies traveling together, one smaller and more volatile, the other dormant. Binary comets aren't unheard of. In 2016, the Rosetta mission to 67P Churyumov-Gerasimenko revealed that its peculiar shape, the famous rubber duck, was actually 2 bodies that had gently merged billions of years ago. If R2 had been born from such a collision, it might still carry hidden structural divisions. But what made R2's case haunting was timing. The secondary anomaly wasn't visible before perihelion, nor during its bright phase. It appeared only after fading began, as though something had separated quietly when no one was watching. Amateurs, fascinated by the mystery, started stacking old images to search for clues. Some found faint irregularities near the tail's edge, diffuse streaks that didn't align with the main dust stream. Others saw nothing at all. One observer described it perfectly. It's like trying to prove the existence of a ghost using smoke. And yet, the more people looked, the stranger R2 became. Spectroscopic readings from the Terskol Observatory in Russia detected trace quantities of sodium, an element not commonly abundant in most comets. Sodium emission lines usually appear only when material is heated intensely, often through fragmentation or electrical excitation. That suggested active chemistry, or mechanical stress, within the debris field. Meanwhile, a smaller observatory in Italy reported an unusual tail morphology. Instead of a single dust tail, R2 appeared to have two faint tails diverging at a shallow angle, one dust, one ionic. Normally, ion tails point directly away from the sun, shaped by solar wind. But R2's ion tail was twisted, as if influenced by a fluctuating magnetic field or by irregular emission jets. For days, scientists debated whether it was solar interference or intrinsic behavior. Neither explanation fit neatly, and still the hydrogen readings refused to fade. The SWAN instrument showed R2's hydrogen cloud persisting far beyond the expected boundary for a comet of its size. In theory, once the water sublimation stops, hydrogen emission should drop sharply. Instead, the glow lingered, faint but measurable, like a candle refusing to die. This led to a subtle but chilling hypothesis. Maybe R2 had lost its visible nucleus, and all that remained was gas, an invisible ghost of itself, drifting onward. Its matter scattered yet coherent enough to trick instruments into thinking it still lived. In other words, R2 might already be gone, but the echo remained, the faint patch trailing behind its last known coordinates. For weeks, observatories tracked that patch, plotting its motion. It matched R2's orbit almost perfectly, except for a tiny deviation, a lag consistent with dust and small fragments moving more slowly than the parent body. Still, the pattern was too organized for random debris. That's when someone noticed something else. The secondary anomaly wasn't just lagging, it was accelerating. Slowly, subtly, over days, it began to close the distance toward R2's predicted path. If it were dust, it should have dispersed. If it were fragments, it should have trailed farther behind. Instead, it was converging. That shouldn't happen. Not under simple physics. The data wasn't definitive enough for conclusions, only suggestions, hints, and silence. But for a handful of scientists watching the numbers change, something felt uncanny. One of them wrote in a private note, "Whatever that is, it's not behaving like dust." The note wasn't published. It circulated quietly among peers, a digital whisper. The next day, the anomaly disappeared from most observation logs, not because it vanished, but because it moved beyond the range of available instruments. By December, R2 was officially declared too faint for continued tracking. Its residual glow merged with the star field, its orbit defined only by prediction, not by sight. But those who followed it, the ones who had spent sleepless nights plotting coordinates and analyzing noise, couldn't shake the feeling that something about R2 had been different. Not dangerous, just different. A comet that arrived unannounced. That brightened too fast, that hid behind the sun, that refused to fade the way it should. Maybe the mystery ends there, a quirk of nature, an artifact of imperfect instruments, a coincidence of geometry. Or maybe the story of R2 isn't just about what it was, but what it taught us to notice. Because the next time something emerges from the blind zone, glowing faintly, moving irregularly, carrying whispers of hydrogen and dust. We'll remember this one. And maybe, just maybe, we'll start looking not just for what's visible, but for what moves like it remembers being watched. When the sky finally forgot R2, the silence felt heavier than the discovery ever had. One by one, observatories crossed its name off their nightly lists. No more updates, no more coordinates. Just the echo of a green light that had vanished into arithmetic. That's how most stories of comets end, not with fire but with fading. They appear astonished, dissolve, and are folded back into time. But R2 refused to end neatly. Its departure was messy. Its data didn't align. Its light curve refused to settle. And its absence left a trail of equations that didn't quite balance. Somewhere in the archives of the Minor Planet Center, buried among dry reports and observation tables, the last recorded visual measurement sits like a whisper. Magnitude 12.3 diffused. Non-central condensation. Translation, it wasn't just dimming, it was dissolving. After that, it slipped below the sensitivity limits of most instruments. To the naked eye, to telescopes, even to long-exposure CCD imaging, it was gone. But to those who'd followed it from the beginning, disappearance doesn't mean nothingness. It means transformation. When a comet breaks apart, it doesn't die. It multiplies. Fragments scatter along its orbit, each carrying the same momentum, the same chemical code. They become invisible ambassadors of the parent body, a silent chain of icy stones wandering through the vacuum. And so, in the weeks after R2's last sighting, a new kind of search began. Not for the comet itself, but for what it left behind. The process was quiet, almost monastic. Astronomers combed through archival frames, looking for faint smudges that might betray the presence of residual dust or fragments. Software compared before and after images pixel by pixel, subtracting stars, isolating motion. Most frames yielded nothing. A few produced maybes. And one, just one, changed everything. It came from an observatory in La Palma taken 10 days after R2's final confirmation. At first glance, it showed only noise. But when the data was processed, contrast enhanced, background suppressed, a faint streak appeared, moving at roughly the same velocity and angle as R2's predicted orbit. It was small, faint, borderline undetectable. But it was there. The team didn't announce it publicly. They submitted it quietly to the MPC under the designation Provisional Fragment A. No one outside the research circles noticed. To the press, R2's story had already ended weeks earlier. But in the dim glow of that faint streak, the comet's ghost still lingered. The follow-up observations painted a picture more intriguing than anyone expected. The fragment, if that's what it wasn't behaving like debris. Its brightness fluctuated rhythmically, suggesting rotation. Its motion was slightly offset from the main orbital line, consistent with a small independent body, perhaps a remnant chunk of the nucleus. That meant R2 had indeed fractured. And not in the distant past, but recently, perhaps during or just after its perihelion passage, when the sun's heat was strongest. Fragments like this are common. But what caught scientists' attention was the timing. The break likely occurred after R2 re-emerged from behind the sun, meaning the event happened out of sight during the weeks we thought the comet was stable. In other words, it broke while we were watching. We just didn't notice. That revelation spread quietly through observatory networks. Emails filled with cautious phrases, possible secondary nucleus, luminosity variance unexplained, further confirmation required. Each message carried the same subtext. The story wasn't over. Then came another report. This time from a French observatory, detecting what might have been a faint dust arc, trailing several thousand kilometers behind the fragment. That's when speculation turned into curiosity, and curiosity into unease, because that dust arc wasn't aligned with R2's old tail. It was offset, tilted upward relative to the ecliptic by a few degrees, as if something had pushed it sideways. Solar wind? Perhaps fragmentation jets? Possibly something else. No one said the word, but it hung in the air anyway. Acceleration. By December, R2's orbit had drifted beyond visibility, but models predicted its debris field would linger for months, possibly years. And somewhere in that field, amid frozen rocks and vaporized carbon, the fragment continued to move, faint, silent. Nameless, some called it R2A. Others preferred the poetic name whispered in late-night research chats, the Echo. That same winter, a new entry appeared in the automated sky survey logs. A faint, slow-moving object detected in the same general region of space, following a similar inclination, but on a slightly different trajectory. At first, it was assumed to be residual dust, but when its motion was plotted across consecutive nights, it revealed a closed orbit, elliptical, not parabolic. That was odd. R2's trajectory had been hyperbolic, a one-way trip from the Oort cloud and back to eternity. This new object, whatever it was, wasn't leaving. It was bound. The discovery sparked brief excitement among professionals. Perhaps a new asteroid, a leftover body perturbed by R2's passage. But as orbital refinement continued, something stranger appeared. The two paths, R2's and the newcomers, intersected. Not just once, but twice, as if one had slingshotted the other into capture. That shouldn't happen easily. Comets don't capture asteroids. And yet, mathematically, the models showed a delicate gravitational dance. Two bodies briefly influencing each other before diverging again. If true, it meant that R2's breakup had altered more than itself. It had left fingerprints on the fabric of nearby space. By January 2026, both R2 and the unidentified object faded beyond reliable tracking. But the chatter didn't stop. In private research groups, scientists debated whether the anomaly near R2's tail, the one seen months earlier, might have been the first glimpse of that second object. A gravitational partner, a fragment, a coincidence. None of it was provable. But the pattern was hard to ignore. R2 arrives from the blind zone, behaves unpredictably, breaks apart and leaves behind a smaller, slower, bound companion. Something about it didn't feel random. And then came the most haunting discovery of all. The Echo wasn't unique. In early 2026, as part of the Near-Earth Object Twilight Survey, researchers detected a faint inbound body emerging from the solar glare, moving along a trajectory eerily similar to R2's pre-perihelion path. Its designation was temporary, C2026b1. Its brightness, marginal. Its composition, unknown. Its orbital similarity, undeniable. When its preliminary elements were plotted, it traced almost the same corridor R2 had traveled. Same inclination, same orientation, only a few million kilometers apart. At first, this was dismissed as coincidence. The solar system is vast. Alignments happen. But the odds of two comets from the same direction, within a year both passing through the same blind zone, statistically microscopic, that's when the whispers began again. Quiet, speculative, but persistent. Maybe R2 wasn't an isolated event. Maybe it was the first in a train. Comets don't travel in fleets, but they can fragment over centuries, producing a series of related objects, siblings born from a long-ago disintegration. If that's what R2 was, a child of a larger, unseen parent, then B1 might be another piece of that same cosmic lineage, and if so, there might be more. The thought isn't catastrophic, it's evolutionary. Comets like these are part of a larger story, one that stretches back billions of years to when the outer solar system was chaos incarnate, flinging ice and rock in all directions. Some pieces escaped, some stayed, some like R2 wandered for eons before finding their way home again. Now, centuries later, they're returning, one by one, glowing briefly, whispering their histories through tales of dust and hydrogen, and vanishing before we can truly understand them. It's not invasion. It's memory. The cosmos remembering its own debris, but the timing, the precision of the reappearance, the faint echo following R2's wake. Those details linger like a pulse in the background of every new observation. Something, somewhere, is retracing the same path. And though no one will admit it officially, every astronomer watching the inner system right now knows that this story, the one that began with R2's late discovery, isn't over, because comets don't vanish. They just wait for the light to shift. It began the way most quiet revolutions do, with a line of numbers that didn't look wrong so much as familiar. C2026b1 was supposed to be forgettable, a dim point easing out of the solar glare at twilight, just bright enough to scrape into the nightly logs, just faint enough for most telescopes to ignore until it improved its manners. But when the first orbital solutions stabilized, the déjà vu was unmistakable. The inclination was low, not identical to R2's, but close enough to make the hair on the back of the neck rise. The longitude of perihelion lined up within a whisper. The argument of perihelion was off by more than coincidence should prefer, less than randomness usually allows. It fit the corridor. It fit the memory. To the public, that meant nothing. To the small community who had followed R2 from a green whisper to a vanishing, it meant everything. Objects arrived from the Oort cloud like strangers on errandless journeys, angles all over the compass. When two take the same aisle through the solar system in back-to-back seasons, you do not assume fate, you assume family. The word is complex and it means a set. Fragments, siblings, descendants of a larger parent that shed itself across centuries. We know this from meteor showers, the Perseids, Leonids, Taurids, river systems of dust carved by parent comets long since dimmed or gone to shrapnel. But seeing a complex in real time, body after body threading the same blind zone near the sun, ducking our defenses in daylight, that is rarer. It demands attention, and it demands humility. B1 did not announce itself in emerald. It did not glow like R2. Instead, its first spectra sketched a colder personality, dust-rich, gas-shy, a dark stone in a slow boil rather than a kettle hissing. The photometry was reluctant, almost suspicious. Magnitude drifted upward by tenths, then flattened as if the comet were rationing its ice. That difference mattered. R2 had been a lantern, B1 was a coal, and yet the geometry rhymed, the solar elongation on discovery, too near the glare for comfort. The twilight cadence, observable only in the narrow window when the sky is not night and not day, when the atmosphere eats contrast and the mountains eat time. The early astrometry, jittery because the seeing was bad and the object indifferent to being measured. Every frustration R2 had taught us to expect, B1 delivered like an encore. The first good images came from a desert observatory just after sunset. Processed, stretched, and stacked, they revealed a stubby coma grainy with large dust. The tail was short, a broom not yet convinced it should sweep. There was no clean ion spike driven straight from the sun. Instead, the tail lay close to the orbital path, as if solar radiation pressure were shoving heavy grains only reluctantly outward. If R2 had screamed volatility, B1 muttered weight. That distinction gave the dynamicists something to argue over. Dust-dominant comets wear their momentum like armor. Big grains don't drift far, and outgassing jets have less leverage. A nucleus that vents shyly does not yank its own orbit around with non-gravitational forces the way a geyser-ing nucleus does. If B1 stayed dust-heavy, models would settle faster, error cones would narrow sooner, and the story would be patience instead of suspense. But comets are not promises. They are temperaments. A quiet week can turn into an outburst in a single rotation. And when the first inflection appeared in B1's light curve, a half-magnitude jump over a single observing night, the old unease returned. It was not dramatic. It was not proof of anything. It was simply a reminder that even a coal carries flame. The phone started again. Not press lines, private ones. An observer in the south flagged a fainter symmetry on the sunward edge of the coma. Another sent a spectrum with a sodium line rising out of the noise, an echo of the R2 afterglow months earlier. Probably nothing, one email said. Or probably something, another replied. The difference between those sentences is not science, it is appetite. The institutions, the ones we imagine as monoliths, do not move as one creature. They are conversations in motion, MPC circulars pared down to bone, JPL solutions fat with covariance, European networks cross-checking calibration frames and arguing gently about where the uncertainties hide. B1 threaded their machinery quickly. Each night added points. Each morning revised destiny. Within a week, the Moid looked sane. Within 2, the Earth pass looked comfortable. Within 3, the language in the solutions shifted from possibility to posture. Not a threat. But if safety were the only measure, these stories would be short. What made B1 compelling was not danger. It was resemblance. The corridor through the solar glare. The timing just post-perihelion for a first clean look. The way the dust tail leaned into the orbit. The way R2's had during its steadier days. The sodium, if it was real. Even the chatter. The way amateurs and professionals braided their work, each catching what the other missed. In the small hours, in the logs no one reads, the sky looked like it was repeating itself on purpose. That suspicion sharpened when the first high-cadence photometry run stitched a rotation signature out of B1's flicker. The period was slow, longer than R2's guessed wobble, but the light curve had the same telltale flat top and sudden dip pattern that suggests a nucleus with facets. Not a sphere, but a lumpy shard, the kind that fragments leave behind when the parent body breaks and the pieces only half forget the break. No one would publish that as proof, but in the quiet between telescope slews, people whispered it anyway. This feels like a child of something larger. If there was a parent, where did it die? The rational place to look was backward, along the path B1 and R2 had traced toward the sun. Orbital integrations ran the tape in reverse, winding both bodies into the dark, past the glare and out into the long ellipse of time. Their lines converged loosely in the outer system, as loose lines do, at 10,000 astronomical units, where comets incubate in the cold. Chaos owns everything. A passing star 1,000,000 years ago erases any certainty we pretend to have now. Still fired, the patterns landed within the same region of phase space, often enough that the idea of a shared ancestor was not fantasy. It was etiquette. Here the story could have stayed a private fascination. Safe pass confirmed, family resemblance noted, paper drafted, filed, debated. But B1 refused to be purely academic. On a windless evening it brightened again, not explosively but decisively. The coma swelled. The tail lengthened and kinked. A soft fan appeared off the anti-solar edge. A second brushstroke at a shallow angle, delicate as breath. It was not an ion spike. It was dust redirecting along a new jet, a vent that had come awake. The brightness did not roar, it sighed. The comet did not disintegrate, it confessed. The confession was content. Beneath the dust there was ice after all. Maybe it was deeper than R2's. Maybe the crust was stronger. Maybe the spin kept the active patch in shadow until the season turned and sunlight found the seam. Whatever the cause, the effect was the same. A gentle but real increase in non-gravitational force, her fingerprint in the astrometry. A tiny push that telescopes can feel when the math is patient enough. Those pushes are not drama. They are decimals. The A1, A2, A3 parameters adjusted by parts in 10 million. The residuals on nightly fits dropped when you let the comet blow on itself, then rose when you tried to make it purely gravitational again. The universe informing you how it wishes to be described. And with that tiny thrust came the old questions we always pretend to retire and never can. How many did we miss before the vent woke? How many sit in the glare at this very hour, not yet bright, not yet loud, waiting on sunlight to meet a crack? How many fellows in the complex are inbound on staggered clocks, carrying the same family chemistry and the same habit of appearing where our eyes are least prepared to look? Rumor fills the spaces between answers. In the forums where amateurs post their miracles, a stacked image appeared that some claimed showed a faint condensation just sunward of the nucleus, a hint of a fragment, or a trick of processing, or the human brain doing what it always does with noise, trying to make a face. Professionals were kind but cool. Repeatability first. Another night, a different observer thought they saw a short separate wisp diverging from the primary tail by a degree. Jet asymmetry, came the sober reply. Evidence lives in chorus, not in solos. Meanwhile, far from the romance, spreadsheets thickened. An observatory scheduler began to trade twilight time from a galaxy survey into B1's favor. A satellite operator put a footnote in a risk memo about micrometeoroid flux predictions for the spring. Not alarming, just prudent. A university press office drafted a "what we've learned since R2" explainer and cut the scarier sentences. The machine of civilization doing what it does when the sky becomes interesting. Adjusting posture without admitting it is afraid. And the public? They noticed, but not with R2's fervor. B1 did not feed the camera with emerald drama. It did not promise a naked-eye miracle. It was a connoisseur's comet, and connoisseurs are few. In a way, that was a gift. Without spectacle, the work could proceed at its natural speed, immune to the metabolism of virality. The story could be about understanding instead of attention. There is a temptation when two notes resonate to hear a scale. Two comets in 2 years wearing similar geometries can seduce you into hearing a procession, a train sliding in from the deep, each car a fragment with a schedule and a purpose. Resist that. The universe rarely plays songs we can sing along to. But do not resist the other temptation, the good one, to become more vigilant where the last surprise came from. If a corridor exists, we should light it. That is the practical legacy R2 left and B1 sharpened. The twilight is where our next embarrassments will arrive. Build eyes for it, not just one, many. Put detectors in orbit that can stare into the glare without blinking. Fund the unfashionable wavelength bands where hydrogen whispers and sodium blushes. Give time to the amateurs who have proven, again, that attention is not a credential, but a discipline. Teach our alert systems to value faint persistence as much as fireworks. On a late night when the comet had already set, a graduate student finished reducing a week's worth of B1 frames and made a plot that no one will put on a poster. It showed the tiniest curvature in the residuals when the model assumed no jets, and a cleaner line, barely, when it allowed a soft thrust from a vent near the subsolar point. She stared at those pixels until they felt like a confession. Then she closed the window and wrote in a lab notebook Three words that belong to every good season of observation. We're getting warmer. Warmer does not mean solved. Warmer means closer to a truth that still has edges we cannot see. B1 will pass, safe and likely forgettable to anyone who did not stand in the wind and watch a faint smear fight the day. It will fade. The papers will publish. Another season will begin, but the corridor will remain. The blind arc will remain. The memory of R2's echo and B1's Shire answer will remain. And somewhere in the outer dark, the parent that made them, whether a single ancestor or the cruel arithmetic of chance, will keep shedding the evidence of its old fracture into the lanes we travel. When the next object emerges from the light, it may wear a new name and a new temperament. It may be gas loud or dust quiet, coal or lantern, lantern or ghost. The numbers will dress it. The headlines will ignore or adore it. Neither will change what it is, a question. And questions, unlike comets, do not disintegrate. They wait. If you want to understand how fragile our vigilance truly is, you have to step inside the system we built to protect ourselves. Not the telescopes on the mountain or the satellites orbiting in darkness. Those are the eyes. I mean the brain behind them. The network of servers, algorithms, and tired humans that decides which dots of light matter. It doesn't look heroic. It looks like spreadsheets. Lines of numbers streaming from observatories in Hawaii, Chile, Arizona, Namibia, and dozens more. Each column time-stamped, cross-referenced, and color-coded by confidence. The data flows into clearinghouses like the Minor Planet Center or JPL's Small Body Database, where programs sift through it, looking for motion. Every night, tens of thousands of new detections arrive. Most are false. Cosmic rays, noise, stars misregistered as moving points. The first job of the algorithms is to throw almost everything away. Only a few hundred make it through to what the system calls tracklets, sequences of positions that seem to describe the same object over multiple frames. If the geometry lines up, the software begins to guess an orbit. Here's where the miracle and the failure begin to share a border. The math is exquisite, but the inputs are human. A camera miscalibrated by 1 pixel, a star catalog slightly outdated, a wrong assumption about timing, and an entire object can disappear into the noise. The system doesn't know what it lost. It only knows what it kept. Each night's surviving tracklets are scored by priority. The brightest and fastest are checked first. These could be near-Earth asteroids. Fainter, slower objects are left for later, sometimes never revisited. The same rule that keeps the system efficient also blinds it to anything subtle. Comets like R2, faint and hidden near the sun, slip through because they don't behave like ideal asteroids. You can hear the frustration in the people who work here. They don't talk like engineers. They talk like custodians of probability. Every line of code is a compromise between speed and sight. Too strict and you miss the ghost. Too loose and the world drowns in false alarms. Inside this digital pipeline, alerts move faster than thought. When a potential hazard appears, a dot moving too quickly or on too shallow an angle, the system triggers a cascade. Emails to observatories, pings to professional networks, automated tasks for confirmation. If enough follow-ups agree, the object gets a name, a preliminary orbit, and a risk score. This is the moment we imagine as triumph. But most discoveries don't feel like triumph. They feel like noise management. Half the time, someone in a control room is staring at a graph, wondering if the blip is real or if the CCD just hiccuped. Half the time, the blip vanishes before they can check. That's how late detections happen. It isn't negligence. It's bandwidth. To cover the entire sky every clear night, humanity relies on a patchwork of projects. Pan-STARRS in Hawaii, Catalina in Arizona, Atlas in both hemispheres, the Zwicky Transient Facility in California. Each uses slightly different optics, cadences, and thresholds. They complement each other, but they also leave gaps. The worst gap of all is daylight. No ground-based telescope can stare into the sun's direction without blinding itself. That's where space-based surveys are supposed to step in. But even there, we are late. NASA's NEO surveyor is still on the drawing board. Until it flies. Our only steady watcher is the aging SOHO spacecraft, whose sensors were built for solar physics, not planetary defense. It catches comets like R2 by accident in ultraviolet bands designed to study the sun's wind. There's irony in that. Our best warning system for inbound objects is a byproduct of something built to look at the star that blinds us. Inside the pipeline, the moment of discovery isn't cinematic. It's a line of code changing from null to value. Then comes the human step, the analyst reading the report deciding whether to trust the machine. That step, more than any telescope, determines whether a comet gets seen in time. Algorithms don't panic, but people do. And panic isn't always fear. Sometimes it's awe. A faint trail on a monitor can remind you in an instant that your entire planet is a coordinate in someone else's ephemeris. The chain that caught R2 did its job beautifully once the comet was visible. What it failed to do was catch it earlier, before perihelion, when the warning would have meant something. That failure wasn't anyone's alone. It was architectural. Our detection network is built like our species, reactive, not anticipatory. We wait for light. We respond to confirmation. We fear false positives more than we fear missing the truth. When you talk to the engineers behind the new generation of systems, their language changes. They speak of predictive heuristics, of machine learning models that can recognize motion patterns even through glare, of synthetic training data that simulates the blinding geometry near the sun. They want a network that imagines before it sees. Not prophecy, probability. In simulation, these systems work beautifully. In practice, they need funding, patience, and bandwidth. The hardest part of planetary defense isn't computation. It's attention. Convincing a world addicted to immediacy to care about slow emergencies. That's why R2 and B1 matter more than their science suggests. They are narrative anchors, stories we can hold on to. Every headline, every image, every whisper of anomaly becomes a reminder that we're still learning to see ourselves from the outside. Inside mission control rooms, that awareness breeds a kind of quiet pride. The people who work there know that success means nothing happens. No impact, no panic, no fame. They live in a world where victory is silence, and yet they keep watching. Because one night, somewhere beyond the horizon of our algorithms, a faint dot will move the wrong way. And when it does, every piece of this machinery, the telescopes, the coders, the analysts, the amateurs with backyard observatories, will have one chance to prove that silence is earned, not accidental. That's the paradox of vigilance. The better we get at it, the less anyone notices. For now, the system holds. The data flows. The sky remains a spreadsheet, constantly revised. But behind every line of code, there's a human heartbeat that still feels what the equations can't. The awe, the fear, the fragile thrill of catching a whisper from something that could have ended everything. By the time the next object appears, no one will remember the name R2 except the people who stayed up late to watch it die. That's how history works. The sky doesn't keep our names, it keeps our habits. But if you look closely, you can trace how those habits have changed. Every discovery teaches us to listen better. Every near miss, every fading light, tightens the focus of our instruments and our humility. In the quiet aftermath of B1, something shifted, not in the heavens, but in us. It was subtle, like the Earth learning to exhale differently. A new generation of astronomers entered the field. inspired not by spectacle but by restraint. They wanted to watch quietly, to study the intervals between noise. That's where understanding grows, in silence. When you visit one of these observatories at dusk, the first thing you notice isn't the sky but the patience. The domes don't open with urgency. The air hums with calculation. Inside, people whisper about algorithms, camera alignment, star catalogs, noise reduction. It feels monastic, devotion without deity, because they know that what's out there doesn't need to shout. A single photon, captured at the right time, can rewrite centuries. R2 taught that lesson brutally. It reminded us that beauty can hide danger, that sunlight can blind the eyes that worship it. B1 confirmed the echo, that nature rarely speaks once. And together, they forced us to confront an old question dressed in new language. Are we observing the universe, or is the universe testing how well we've learned to observe? There's a strange humility in realizing that our vigilance might be part of the experiment, that maybe awareness itself, the act of watching, is what the cosmos wanted to teach its temporary inhabitants. Because when you think about it, everything we've built, telescopes, satellites, spectrometers, is just a translation of wonder into hardware. We're trying to measure a feeling. We want to know how all behaves under light. That's what makes this kind of science holy, even when it wears a lab coat. Somewhere, an old radio telescope still listens to the hiss of the sky, picking up remnants of R2's hydrogen, stretched and weakened by distance. Those signals are almost meaningless now, buried in solar noise. But to the researcher staring at the screen, that faint curve is a message. You looked in time. And that's enough. In another corner of the world, an undergraduate runs simulations of comet families, plotting how fragments separate over millennia. On her monitor, thin white lines stretch outward like veins of possibility. When she zooms out far enough, they resemble a network, a map of motion so intricate it looks deliberate. She smiles, not because she believes in patterns, but because she believes in persistence. And persistence, not certainty, is what defines civilization. Our ancestors painted comets on cave walls. We write equations instead. The grammar changed, but the awe remained intact. That's the quiet thread through all of this, awe as inheritance. Every telescope built, every budget approved, every late-night observation under red light, they all begin from the same pulse that once made people kneel before fire in the sky. We no longer call it prophecy, we call it data. But the reverence is the same. In that sense, R2 and B1 weren't warnings or omens. They were invitations to keep paying attention. We often talk about the universe as something vast and indifferent, but maybe that's not the whole story. Maybe indifference is its way of giving us freedom, the chance to define meaning for ourselves. Because if the cosmos cared too much, we'd never have learned to care at all. Silence is permission, and in that permission, humanity built its greatest mirror. Think of it, a species that evolved from dust, learning to trace dust across billions of kilometers, trying to catch it before it fades. That's poetry pretending to be engineering. It's easy to dismiss our efforts as futile, tiny creatures measuring infinities, but the futility is the beauty. The attempt itself is proof that consciousness can rise from chaos and look back at its origin without despair. Maybe that's what every comet teaches us. Not fear, not survival, but continuity. When one fragment burns away, another follows. When one generation fades, another looks up. The sky doesn't repeat events. It repeats opportunities. The question is whether we'll recognize them in time. If history holds, there will be another discovery, another object emerging from glare, another pattern too precise to be coincidence. The headlines will sound the same. The data will look familiar, but somewhere beneath the numbers, a quieter realization will form. We are part of the system now. We are not bystanders. We are participants in the universe's ongoing act of self-awareness. And maybe that's the only defense that ever mattered. Not technology, but attention, because you can't be destroyed by something you've already learned to see clearly. Awareness doesn't prevent collision, but it transforms what collision means. Even if the sky ever did fall, we'd still be looking up, trying to name it as it happened. That's the legacy of R2 and B1, not their orbits, but their afterglow inside human thought. They taught us that vigilance can be beautiful, that silence can be instructive, and that sometimes survival isn't about avoiding impact. It's about understanding the moment before it arrives, so when the next faint visitor appears, and it will, someone, somewhere will be awake, staring through the twilight, remembering the comets that came before. And they'll whisper what every astronomer eventually learns to say, "We've seen this corridor before." And then, as always, they'll aim the telescope, press the shutter, and listen for the sky to answer.